Hi, and welcome back to my Physics Online video lecture supplement series. In today's video, I'm going to continue my discussion of the second lecture set in the Introductory Physics 2 course. This is a lecture set which is basically covering electricity and electric fields, the introduction of charge and electric fields and Coulomb's law and Gauss's law. And in today's particular lecture, I'm going to talk about electric fields. So with that said, so far we have encountered two types of force which can act on an object at a distance. In other words, these are non-contact forces. The two in particular that I'm thinking of are gravity and the electrostatic force. With gravity, we had Newton's law for universal gravitation. For the electrostatic force, we had Coulomb's law. And the basic idea behind these two forces acting at a distance is that the objects that are applying the force do not have to be in physical contact by, for example, touching the object upon which they are applying the force. So, in other words, the Earth can apply a force of gravity on the Moon, and the Moon likewise applies a force of gravity on the Earth, and the two aren't in contact with each other. They're not physically touching. And forces of this type are what we call field forces. And basically what this means is that we can associate some field with these forces which permeates the area surrounding the object. And in fact, the two that we've encountered so far, gravity and the electrostatic force, the field in question permeates all of space around the object, and the strength of the field gets weaker as you get farther away from the object. So the strength falls off like 1 over r squared. And an application of the electric field specifically, although you can sometimes find a way to make it work with gravity by modifying a little bit, is what's called Gauss's law, which is what will be the main topic of the third part of this lecture set. So to get from Coulomb's law to Gauss's law, we have to know something about electric fields, and that's what we're going to do today. So the electric field was first developed by Michael Faraday, and what he did was basically he said there must be an electric field which exists in the space anywhere near a charged object. He didn't necessarily posit the gravity field, but it can work the same way. There's a gravitational field which exists in the space near a massive object. And what these two fields do, the electric field and the gravitational field, is they can act upon any other objects within the vicinity according to either Coulomb's law or Newton's law of universal gravitation as appropriate. This means that the electric field will interact with any other charged particles that are in the vicinity. It doesn't interact with the object that's actually generating the field. And the field has to exist in the same location as whatever object it is acting upon. So if I have an electric field that is acting upon a proton, it's got to be generated by something other than that proton, and it's got to exist in the same location in space as that proton exists. Basically what this means is that you have to have a second object, a second charge to generate an electric field. And so usually we take the first charge in a problem and say this is the source of the field, and then we place additional charges in or around the field and see how it interacts with them. with that said, Newton's third law still does apply to the source object. So if I have a proton, which is generating a field, and there's an electron nearby, there will be a force that acts upon the electron, and the electron itself is also generating some field which acts upon the proton. This is true, by the way. Everything that I've said is basically true for gravitational fields, with the exception being that instead of caring about charge, we care about mass. So the gravitational force acts on a massive object. It's got to be applied by the local gravitational field, not the object that causes the field. And the field of gravity cannot interact with the object which is generating that field. One way in which we probe the electric field is that we can use a concept called a test charge. And basically there's sort of the experimental or practical version of what it counts as a test charge, and then there is a theoretical version of what would count as a test charge. So what a test charge basically is supposed to do is it's supposed to be used for measuring the strength of the electric field. Experimentally, the way that we do this is we need a charge that's very small compared to whatever the source is that's generating the field. And so basically what that does is anytime that you add charges into an existing field, those charges come with their own field, and the existing field and the new field that's set up by these additional charges basically add together via the superposition principle. So experimentally, we need a very small charge. Sometimes we denote it by little q naught, and it has to just be much less than the source charge, the total charge of the source, big Q. And so what this means is that the test charge is sufficiently small such that it doesn't rearrange all the charges from the source charge itself. So for example, if your source charge is a large charged conductor, all of the charges are sort of sitting in the surface of that conductor. They can move about freely. You want a test charge that is small enough that if you put it nearby the conductor, all of the other charges that are in the conductor aren't necessarily going to flow to the far or near side of the conductor. There's not going to be appreciable movement and therefore appreciable alteration of the existing field. Theoretically, the charge of Q naught does not matter because we basically can pretend that it is not coming with its own field, since the purpose of it theoretically is just to test the existing field. Sometimes we do something convenient like assuming that this test charge is 1 coulomb, which is actually an enormous charge in real life. In experimental terms, we basically need it to be a very weak charge, so that the field generated by it is very weak or very negligible compared to the existing field. Theoretically, it doesn't matter as much because we treat the test charge as being the only charge that doesn't generate a field. And so if we use a 1 coulomb test charge, then the units end up working out nicely. And the reason for that is that the electric field itself is defined in terms of the force which acts on the test charge. So here is basically how we define the electric field with regard to the test charge. The electric field is the force that acts on the test charge divided by the magnitude of the charge. Or in other words, force is equal to charge times field. So we can use Coulomb's law And if you have a given charge, little q, a single point charge, it's going to generate a field whose magnitude is given by this equation. This is Coulomb's law, except for that instead of having q1 times q2, we just have little q. Because again, we're not concerned with the force between two charges here. We're concerned with the field that's being generated by a particular charge. And the units that go with electric field, or the units for the magnitude of the electric field in particular, are newtons per coulomb. So this again is why it's sometimes useful to have a theoretical test charge of 1 coulomb. Basically, then you can divide the force that is experienced by that charge by 1, and now you have the strength of the magnetic field because your charge is 1 coulomb. As for the direction of the field, see, the field is actually what's called a vector field. It means there's vectors. So the electric field at a given position actually has a vector value, magnitude plus direction. And so the direction is going to be determined by the sign of the source charge. And we'll look at that in a moment. Basically, if we have a positive source charge, then the field points away from that source charge. If we have a negative source charge, then the field points towards that source charge. And here that's actually shown in a simple diagram. Here's a positive source charge, here's a negative source charge. Now this is granted multiple negative charges and multiple positive charges, but the field in general still will point towards the negative and away from the positive. If you want to get the total field by a collection of point sources, you basically just figure out what the field is from each individual source, and then you add those fields together by using the superposition principle. Very often we use some properties of the system like symmetry. If the charges are distributed about a sphere and they're equally distributed, then symmetry says in the middle of the sphere there should be 0 electric field. Outside the sphere, the field will look the same as if all of the field was from a single point charge in the center of the sphere. We'll get to that later though when we discuss Gauss's law. Let's look at a few examples before going on to how we can actually visualize electric fields. Alright, so in our first example, we are given a test charge of 1 nanocoulomb, and we're told that it experiences a force of 50 newtons at its location. So we want to know what is the field strength. So E is the field strength with no vectors, the magnitude of the field, is basically the magnitude of the force divided by the charge on the test charge. So that is basically 50 newtons divided by 1 times 10 to the 9, 1 times 10 to the minus 9 coulomb. This is nanocoulomb, is the same as 1 times 10 to the minus 9 coulombs. So this is 5 times 10 to the 10 newtons per coulomb. For our next example, we want to know what is the magnitude of the electric field 30 meters from a conducting ball of radius 0.1 meter, which has a total charge of 1.0 coulomb. So here is our conducting ball, and there's basically charges in it. The charges, we will find out later, tend to be equally distributed in a sort of a shell around the surface. And basically this object can be reduced to act in the same manner, as long as we're talking about something that's far away, like over here. It acts in the same manner as if we have a single point charge located in the middle. So this right here is a distance 0.1, this is a distance of 30.0 meters from here out to here. This distance is much smaller than that, basically 0.1 meter. So the force in general from Coulomb's law should be negative K times Q1 times Q2 over R squared. And this really can be altered now because this has a total charge of Q equals 1.0 coulombs. And so basically we would say something like force equals K times Q naught over R squared. And if we wanted to find the electric field strength, that's force divided by test charge. So K Q times little q over R squared times little q naught, that is. So those cancel. You're left with that the electric field strength must be the Coulomb's law constant times the charge of the source divided by the distance squared. So that is, if you'll recall, that the Coulomb's constant K is equal to 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. And the big Q, charge of the source, was given as 1.0 Coulomb. And then the distance away was given as 30.0 meters. And so we square that. So this is approximately 1.0 times 10 to the 7 newtons per coulomb, because we have about 9 divided by about 900, and then that's times 10 to the 9. One last quick example is that we have a little drop of water. It's got a given mass 1.00 milligrams, which is the same as 1.00 times 10 to the minus 6 kilograms. And then we're given the electric field strength, told that it's pointing upward, and we're asked what the charge must be on that drop of water. And since it's suspended in place, Newton's first law applies. So that means that the sum of forces should be 0. So that means that Q for the water, the charge of the drop of water, times the electric field strength minus the mass of the water times G is equal to 0. So I've kind of converted from vector form into scalar form here. So the water charge must be the mass of the water times the gravitational acceleration divided by the electric field strength. So that's 1 times 10 to the minus 6 kilograms times 9.80 meters per second squared divided by 1.50 times 10 to the 6 newtons per coulomb. So that gives us a total charge for the water droplet of approximately 6.53 times 10 to the minus 12 coulombs, which is basically 6.53 picocoulombs. So that is how much net charge is in this water droplet. And of course it must be a positive net charge in order for this force to be upward acting. Alright, so now that we've discussed very briefly what the electric field is, it's worth uh, discussing how we can actually visualize the electric field. And one tool for doing that was again introduced by the same guy who came up with electric fields to begin with, Michael Faraday. Basically, if we want to visualize an electric field, we use what are called electric field lines. And there's a few rules that go with these electric field lines. First of all, the field everywhere is tangent to the field lines which radiate out from or into a charge in 3 dimensions. They radiate out from positive charges, they radiate into negative charges. And so the field is everywhere tangent to this line, so if the line happens to be moving in this direction, then the field right here also points in this direction. Second rule is that the number of field lines per unit area through a given surface has to be proportional to the strength of the field in a given region. So in other words, you see that there are more field lines for this charge than there are for this charge. So if figure B and C are both to scale, then this charge probably has about twice the magnitude as this charge does, because there are twice as many lines radiating out from it. And similarly, that means that the field here is twice as strong as the field at a comparable distance away from this charge. And similarly for this one, albeit in the opposite direction. So if you have field lines close together, then the electric field is strong, and if they're far apart, the electric field is weak. So that basically is the set of rules that goes with the electric field lines generated by a single point charge. And I should add to this that these drawings that are made are actually basically a 2D projection. The electric field itself actually exists in 3 dimensions, so there's also a field line radiating out and into the page here, radiating out at an angle, etc. So we're just looking at the field lines in the XY plane, but there are in fact also field lines that have Z components. So far we've been treating our elements of charge as if they are still discrete. In other words, you have a clump here, you've got a clump here, you've got a clump here. If we want to figure out what happens if we have a continuous charge distribution, we basically say that each of these clumps has only a very small charge that's being contributed. So we take the limit as delta Q approaches 0, and so that's basically the equivalent of transforming from delta Q into dQ and from delta E into dE. If we want to get the total electric field, we basically get E from the integral of dE. In other words, the total electric field is the integration over the differential electric field. And that basically is going to have some equation that maybe looks something like this. And at this point, we have to pay more attention to what the geometry of the situation is. Do we have a 3D charge distribution? Can it be reduced to 2D? Can it be reduced to 1D? So in 3D, oftentimes you'll have a volume density rho sub E, which is the total charge divided by the volume. And very often this charge distribution will have some function. It might be charge is distributed as a function of R, or it could be some constant times 1 over R, what have you. And so this distribution, this density function, is multiplied times the volume, and that gets you your differential charge. And so dQ is rho dV. If you're in 2D or 1D, then the same argument applies, but instead of having a charge per unit volume, you're going to have a charge per unit area, or a charge per unit length. And so you'll end up with a sigma dA or lambda dL. So you're going to end up integrating over some function and then finding the charge that way. All right, what happens if we want to actually draw the electric field lines for multiple charges? Well, we basically can follow the procedure described on the previous few slides, except for that we basically move the point P around until we've got the field at quite a few different points, and then we just draw the field lines based on that. So this actually is also how you find it in the laboratory, except for that there's sort of a twist. We need to know something about voltage first, but you basically measure voltage drops and find where the voltage drop is 0, and then you draw what's called a equipotential surface or an equipotential contour, and then the field lines are perpendicular to those everywhere. For our purposes, without knowing anything about voltage and potential, what do? Well, we basically go back to our distribution, and we treat the distribution as if it's whatever charge configuration we have. And then we basically move our point P around and figure out what is the electric field doing at point P. And then we draw our lines accordingly. Now, with that said, that's actually a pretty complex way of going about things. There are a few simple rules, or relatively simple rules, that will make this process a lot easier for us. If you have multiple charges, then the field lines that come from these charges are going to obey, first of all, the rules already described, but also that the field line for any group of charges always has to begin on a positive charge, and it always has to end on a negative charge. All right, if there are no negative charges for a field line to terminate on, then that field line has to basically just continue off into infinity. Second of all, the number of lines drawn from a positive charge or drawn to a negative charge have to be proportional to the magnitude. I kind of discussed that briefly in talking about field lines for a single charge. I'll say it more explicitly here. If you decide to draw your field configuration so that you have 8 field lines coming off of a point charge of 1 coulomb, then a point charge of 2 coulombs needs to have 8 times 2 or 16 field lines coming out of it. And if it is isolated, those 16 field lines are probably going to radiate basically with a proportional spread. In other words, same angle between each line. At least initially it will be. The third rule is that field lines do not ever cross each other. So field lines are allowed to bend, but one field line cannot actually intersect a second field line. It has to bend around it, or else you've drawn something wrong. And before I go on to show a few simple field line configurations, I should note that the electric fields themselves, the electric field lines themselves, don't really represent any material object. They don't represent, for example, the path that a charged particle will necessarily take in an electric field. They just represent locally the direction and, to some extent, the magnitude of the electric field. And so that means that if you place a particle somewhere within your electric field lines, you can get a guess at the direction in which the force is going to act. You can guess at how strong the force is going to be at that point relative to elsewhere. You can't use the field lines to predict this is the path that the particle will follow just by saying, oh, it's going to follow along this field line, because it won't follow the electric field lines. All right, the simplest thing you can do with multiple charges is what's called a dipole. And this diagram actually shows a simple dipole. It basically consists of two charges. The two charges have to have opposite signs, so this one's a positive charge, this one's a negative charge. If you fix the two charges in place, you've got what's called a permanent dipole. And let's look at what the fields are doing. So every line that's coming out of this positive charge has an arrow that's basically pointing away from the positive charge. Every line that's going into the negative charge has an arrow that's pointing towards the negative charge. So this means that the field lines are originating with this charge, they're terminating with this charge. Notice that between the two charges you have quite a few field lines per unit length, or really per unit area. And in fact, if we could do this in 3D, it would be per unit volume. There's quite a few lines as compared with, say, over here on the back side of the positive charge, where you might get this one field line, but there's not, you have to move up quite a ways before you get to the next field line on this scale. And so what that's implying is that the field is actually very strong here right between the two particles, and it's very weak out here where, for example, the negative charge is shielded by the positive charge and vice versa. Second, if you were to count how many lines there are from each of these two particles, they have equal magnitude. You'll notice that there's the same number of lines going into the negative charge as there are coming out of the positive charge. Finally, if you go very far away, over here for example, or in fact off the screen, the separation distance between these two becomes very small compared to the distance away, and so the electric field approaches a strength of 0. So if we were to keep drawing this line out here, it would maybe come to here. This one's actually kind of curving. It's maybe going to end up curving around and eventually becomes this line that's coming into this charge. So pick a random point out here. Odds are you're not going to be anywhere near a field line. Hence, your electric field strength is 0. And ditto for if you go very, very high up here. You end up with odds being slim of being on any field line. So again, your electric field strength would be 0. Alright, so let's look at a slightly different version. What happens if instead of having a dipole, we have two charges of the same strength? So again, you'll notice that the two charges, so they now have the same sign. You'll notice that in all cases, the line is coming out of the charge, not going into it. The arrow points away from the charge. Again, you'll notice that there's the same number of lines that go with each of these two charges because they have the same magnitude. And you'll also notice that none of these field lines actually cross each other. They basically will bend away from each other. So if you were to put some test charge right here in the very middle between the two, it would read a field of 0. No field line makes it here to the very middle. If you go very far away, such that the distance between the two gets to be small compared to how far away you are, then it starts to look the same as if you just had a single charge in the middle with a magnitude of 2 times whatever the charge of each of these individually is. So that's what happens when you have two of the same sign and same magnitude. Okay, what happens if you have two that have opposite signs but not the same magnitude? In other words, maybe there's 2 positive charges for every 1 negative charge here. Well, basically you have to draw such that there are twice as many lines coming out of this positive charge as there are terminating in this negative charge of half the magnitude. So every one of the lines that terminates on this negative charge could be drawn coming out of the positive charge, and then you have to draw an additional number of these lines coming out that do not terminate anywhere. They just go off to infinity. And if we go very far away, these things that are going off to infinity start to look very much like the same configuration that you would have if you just had a single charge of magnitude 2 minus 1 equals 1. So 1q located here in the middle. You will notice that between the two there's still a stronger field than behind either one. So there's still some shielding going along. You'll notice that the field strength near to but on one side of the positive charge is going to be different than near to but on the side of the negative charge. It's virtually zero here, and in fact there is some point over here at which you do get zero. We even actually calculated something like this in the previous set of lectures. Alright, let's do one last set of field lines, because this one's also a pretty important set of field lines. What happens if you have two long parallel conducting plates? By the way, we will study what happens when you have this configuration in a future chapter. This is basically a parallel plate capacitor. And what happens is, if they are two long parallel plates, then you should have, and they're conducting, you should have an equal charge distribution along the entire pair. And at least so long as you're not near the edge of the pair, you should be able to just draw fields as being straight lines going from the positively charged plate to the negatively charged plate. If you get towards the edge, you get what's called an edge effect, where these straight lines start to actually exhibit some curve. And in fact, you can draw some lines coming in and lines coming out here, and they'll sort of curve around like so. So you do get edge effects because there is in fact some curving field out here. So that's all I wanted to say about electric field lines. Sort of the last thing I wanted to talk about in this lecture is a historically important experiment called the Milliken oil drop experiment. And what this experiment did was it measured the approximate charge of a single electron. And the way that it worked is basically as follows. So here's your setup. You have a pair of these charged plates, so you can already imagine that the field lines look something like this between those charged plates. In 3D, you just get additional parallel straight lines coming out of, still running from what looks like left to right, but the line would be sort of 2 inches above this plane, for example, and 4 inches above this plane rather than 2 inches and 2 inches and 2 inches, for lack of a better way of describing a 3D phenomenon with a 2D diagram. Okay, so be that as it may, you have these two parallel plates. One is hooked up to a positive terminal, one to a negative terminal for a battery. So that means that this plate is going to have a positive charge, this one's going to have a negative charge. So the electric field lines are basically pointing down. In fact, in the same direction as this V arrow for velocity. And what he did was he had a little atomizer from which he could spray oil droplets that could, some of them, fall through a pinhole in the top plate. And basically he could choose to charge or not charge the plates as needed. So he basically did this with the plates charged, then he did it with them not charged. And last but not least, he used X-rays to ionize the air around the droplets so that the droplets would have a charge. So the droplets have a charge, the plates may or may not have a charge. Okay, once that has been done, he also would be shining a beam horizontally, which in this drawing, given that this is sort of horizontal direction, horizontally would therefore mean going into and coming out of this page. And that's just to illuminate the drops as they fall against some dark background. So maybe he has like a dark room, a black wall or whatever over here, and he's shining a beam of light into and out of the page. And he could look at the droplets by looking through the telescope, which is aimed here between these two plates. And what he does is he can watch these droplets, and they actually fall very slowly, about 0.01 centimeter per second. Watch these droplets and see how slowly they're falling. And the way that this experiment works is when you don't charge the two plates, the only force that acts on the droplet is gravity and the buoyant force and the air drag. So gravity, of course, is going to be the mass of the droplet times g. Mass of the droplet you find by figuring out the volume and density of the droplet. That's relatively easy to do. Then you have the buoyant force, which you can treat as a modification of the gravity force. And then the drag. And the drag, of course, is going to have some form like negative b times v. And if you charge the two plates, then you get an additional upward force. And that upward force is from basically the electric field acting on the charged particle. And so what he did was, in each of these two cases, with no charge on the plates and with charge on the plates, he figured out what the terminal speed was. So recall that the terminal speed looks something like this in the absence of that additional force from the E field. If you add the E field in, then you end up with an equation that looks like this rather than an equation that looks like this plus mg. So either this is 0 or this is E as appropriate. And what that means is that he's able to determine what the drag is, and that he does from the known terminal speed. And by having done that, he can get what the drag coefficient is. Then he's able to determine the charge Q, which is placed on the droplet itself. So Q is the charge on the droplet, E is the electric field from between the two plates, this is the force of gravity, this is the drag force. This is what happens when there is an electric field present. The drag force is downward because the particle is actually moving upward. This is the drag force when there's no electric field and the particle is basically moving downward. Okay, these two drag forces are actually, in fact, different values because there will be a different terminal velocity thanks to the fact that the electric field is not just twice whatever the force of gravity is. It can be very strong or 1.5 times the gravity, it can be 5 times the gravity, etc. In any case, once you've done all this, you've solved for Q, what this guy did, what Milliken and his colleagues found, was that no matter what he did, there was always some integer value of the electron charge E that gave the total charge of a droplet. So Q is N times E, where N is some integer number. And so basically he just measured what the value of E had to be by changing what the values of N were and finding, okay, well, if the value of N is 1, then we get a terminal velocity which is so and so, and if it's 2, then it's such, and so on. And so he measured the value of E at 1.6 times 10 to the minus 19 coulombs. So now I want to work through a couple of quick examples here. The first example involves this continuous ring of charge, and we are given some radius, in this case lowercase a, and a total charge of big Q that's placed on the radius. And what we want to know is, first of all, actually determine what the electric field at this point P is, given that it's some distance x away from the center of the charge, from the center of the charge ring. And then B, what would we change in our approach? In other words, just discuss what happens if we were to chop this ring in half and remove the top half so that only this bottom part of the charge is left. For this ring of charge, if we wanted to find what is the total electric field at point P, basically you get some differential field dE, which is caused by a differential charge dQ. So dl, differential length of the ring produces, or contains, I should maybe say, a differential part of the charge. So what that means is that we can write the differential field is going to be 1 over 4 pi epsilon naught times dq over r squared. And we can basically note that dq is basically going to be q times whatever this dl divided by the total length, which is 2 pi times a. And we're going to represent that basically by using a lambda dl. So lambda is the total charge of the ring divided by the total length, that is the circumference of the ring. So dE we can therefore write as 1 over 4 pi epsilon naught times lambda dl over r squared. Now, the next thing to note is that if we look over here at the symmetry of this problem, let's say that we look at the the y component of the field here at point P. Well, from this section dl, we're going to get a y component that's straight down. For this section right here, dl, we're going to get a similar component that is actually straight up. dE perpendicular will be up here. And in fact, that will be true for any slice of this ring that we take. There's always going to be a sort of opposing slice or a supplementary slice, which is going to have a upward for every downward or a downward for every upward perpendicular component. So when you add up all of these little slices, which is what you do when you integrate, all of these dE perpendiculars or dEy components are going to cancel with each other, and you're going to end up with only needing to find the x or parallel component, for lack of a better term. So we'll call this dEx. This is really more like a dEy. And having said that, we can therefore write that the total electric field should in fact be equal to the total x part of the electric field. And so we're basically just integrating over dEx. And so that's equivalent to just integrating over dE times cosine of theta. So theta is this angle that we're choosing here. You could also think of it as being an angle within this ring as we integrate around the ring. So we basically can say that in this case, theta right here is going to be such that cosine theta equals equals x over r, adjacent over hypotenuse. And r, you can see, is a squared plus x squared. So this is square root a squared plus x squared. Therefore, if we want to try to figure out what the total field is, we can rewrite it down here as E equals lambda over 4 pi epsilon naught times x over x squared plus a squared. That's the r squared term from our dE, times the integral of dl. And we're integrating from 0 to 2 pi a. So we're basically going to integrate dl around this whole circle. In this case, we don't actually use any kind of angular coordinate in here, although we might have redefined dl, for example, as dl equals a times d phi, where phi is basically this angle, phi. And you will see that in this case we'd be integrating from phi equals 0 to phi equals 2 pi, and so you'd get an equivalent expression down here to what we have. So that's an alternative way in which we could be solving this. Either way, none of this stuff is a function of dl. None of this stuff is a function of this angle phi. So the integral is rather easy. You just get from L equals 0 to L equals 2 pi a. This integral dl is just going to give us an L. And so our E field should be lambda over 4 pi epsilon naught x over x squared plus a squared times 2 pi a minus 0. And again, lambda we defined as q over 2 pi a. We have a 2 pi a times lambda. That means that it's equal to q. And so that means that this total E field should look like q times x times basically 1 over 4 pi epsilon naught times x squared plus a squared. And that is what our electric field strength is going to be. Again, note that this is sort of on point with the center. So this line that passes through the point passes through the center of the ring parallel to x. What would happen, the second part of the question, what would happen if we chopped the top part of the ring off? The question becomes a little more complicated then, because if we chop off this top part of the ring, let's say that we were to remove all of this, you'll notice that we've now removed the supplementary pieces for all of these dl's. That means that this term right here no longer is going to have its supplementary piece down here to cancel with. And so in fact the net E field is going to be pointing off in some direction. It's possible it'll point off like that, for example. And we will no longer be able to use E equals EX. So we'd have to go back here and actually integrate over dE. Our limits of integration would now be from 0 to pi rather than 0 to 2 pi if we were to use an angle. And this r squared term would be a squared plus x squared still. But now the a squared term, we might actually have to pay attention to y's and z's over here. Again, if we're just using dl, shouldn't matter. We should just be chopping off the top half. We should be able to integrate from here around the circle to here, figure out what is the y component over here, figure out what is the x component. You can still see that any z components will actually cancel out. Only the y components are not going to. So that's what's going to change. Other comment on this, going back to the full ring, notice what happens if x is much greater than a. If x is much greater than a, then we can do a little Taylor expansion of this term here, and of this and this term here will end up canceling with some components down here, to where basically this will end up looking like q over 4 pi epsilon naught times x squared, as it turns out, which is in fact the same form you'd get if you had just a single point particle located right here. So that's, we're talking if point P is somewhere way over here, as opposed to in close like this. Okay, so that is the first example. Our second example is perhaps a little familiar because we actually did this in the context in the last set of lectures of just figuring out how much force would be acting upon a charge that's located here. So now we want to repeat but find what the electric field is here. So here's our diagram, and what we want is the electric field at this point P. First thing that I notice is maybe before noticing anything I should just set up a simple differential dE. So dE is going to look like 1 over 4 pi epsilon naught times dq over r squared. And I'm going to define a term lambda to be the charge per unit length. And so what that basically means is that dq is going to be lambda times dy. So that means that my differential electric field should look like 1 over 4 pi epsilon naught times lambda dy over r squared. Okay, now, as I was saying, the first thing that I notice upon looking at this is that I can draw another dl, or another dy, down here. And this dy down here should be contributing an electric field this way. We'll call this dE prime. Call this dy prime. That prime is not for a derivative, it's just to distinguish it from this dy and this dE. Should be the same differential length as this. I've chosen it to be at the same angle theta. That means it's the same distance away. Everything's the same, we're just on the opposite side of this axis of symmetry, this x-axis. And so if you break up this dE prime into components, there's a dE x prime component, and there's a dE y prime component. And the dE y prime component is the same magnitude in the opposite direction as dE y. The dE x prime component is the same magnitude and the same direction as dE x. So collectively what this means is that instead of trying to find the total field and integrating for all of y and for all of x, we should be able to see that by symmetry, the total E field, total E, should be Ex I hat. So there's not going to be any y components. So in other words, Ey is going to be 0 when we integrate everything. What this means is that instead of using this differential dE, we can use the differential for dEx, because Ex is going to be the integral of dEx. And dEx is the same thing as dE times, looking at this triangle, here's theta, here's x, here's r. So this goes with cosine of theta, this goes with sine of theta. So dEx is really dE times the cosine of theta. Draw a little division line here. Let's go ahead and therefore write everything out a little more explicitly. E, which is the same as Ex in this case, should be the integral of dEx. And looking at what we have that's constant, we'll just go ahead and pull some stuff out. The lambda, the 4 pi epsilon naught can all come out. Put our integral here. And right now what we have basically is dy cosine theta over r squared. Okay. Now, looking over at this diagram that we have here, I notice that theta, y, and r are all coupled. R is in fact x squared plus y squared and then a square root. So r is a function of y, and we can see that y is in turn a function of theta. So we should convert all these variables into either being all y's, all thetas, or all r's. And we're going to choose theta. So what is that going to look like? Well, I see that the sine of theta is basically going to be y over r. And I see that the cosine of theta is going to give me x over r. And last but not least, I see that the tangent of theta should give me y over x. Okay, so with that thought in mind, what I really want to be able to do here is take a dy d theta and not have any sort of coupled variables in it. So I'm going to use this equation for that because x is constant. X is this distance right here. It doesn't matter whether we're talking about this differential, some differential way up here. X is the same. So according to this, y is equal to x times the tangent of theta. All right, so what we're going to do here is we're going to take dy by d theta. And so that should be x times the derivative of tangent. And of course, the derivative of a tangent, 1 over the cosine squared of theta. All right, so that means that we can basically rewrite this differential so that dy is equal to x d theta divided by the cosine squared of theta. All right, now the next thing that we've got to deal with is the fact that we have an r squared down here in the denominator. And r, again, we're going to want to put r in terms of theta, but we want to put it in terms of theta and x. So we're going to use this term for r. So this right here is how we got dy. This right here is how we're going to get r. So r is equal to x over cosine of theta. And so what that means is that r squared should be x squared over cosine squared of theta. So going back to this integral, we have basically e is going to be lambda over 4 pi epsilon naught integral. Let's go ahead and do our substitutions. So we had a cosine of theta originally. Our dy means that we have to put in an x d theta over cosine squared theta. And then our 1 over r squared term means we have an x squared divided by cosine squared of theta term. So there's a cosine squared theta here, there's a cosine squared theta here, there's an x squared, there's an x. That means that this whole integral is going to reduce a bit. So we can now write e is lambda over 4 pi epsilon naught. I'm going to pull the x's out, x over x squared, so that basically means there's an x that goes right here. And then what's left over is a cosine of theta d theta. So what are our limits of integration for this thing? Well, if we were integrating from y, they would be from minus infinity to plus infinity. But we're not integrating over y, we're integrating over theta. And when we get to the infinity point here, this line right here is practically a vertical line, which is the same thing as 90 degrees. And this one is a vertical line in this way, which is minus 90 degrees. So in terms of radians, it's minus pi over 2 to plus pi over 2. Okay, this is a simple integral. As you know, integral of cosine theta d theta is equal to sine of theta. We're evaluating from minus pi over 2 to plus pi over 2. So sine of pi over 2 is equal to 1. Sine of minus pi over 2 is equal to minus 1. We're subtracting these two from each other. So what I end up getting here is that E is equal to 2 times lambda over 4. So lambda over 2 times pi times epsilon naught times 1 over x. And that then gives us what our electric field strength is at point P. And again, if we wanted to write this as a vector, E, the vector, is basically going to look like lambda over 2 pi epsilon naught. This is a really bad looking epsilon times 1 over x, and then the direction is actually the I hat direction because it's in the, it's parallel to the x-axis. So this is E expressed as a vector. Okay, now the question, the extension of this question that I asked, part B, is what happens if we were to chop this thing in two? Okay, so if I chop this in two, it's like eliminating this bottom part. If I eliminate this bottom part, it's like eliminating all of these d prime components here. That means that now we're going to have to actually deal with a dEy component. And so we would end up in the end having an E field that looks like E sub x I hat plus E sub y j hat. And in fact, E sub y you can see is going to be negative. This basically means that we'd have to go back and actually integrate, this time from negative pi over 2 to 0. So we've changed our limits of integration. Everything else that we did for Ex is still valid. So the Ex component is just going to be half of the Ex component here because we have only from minus pi over 2 to 0, and so this term actually would be a 0. So Ex in this case is going to look like pi times divided by 4, lambda divided by 4 pi epsilon naught times 1 over x. And so that's what's in the I hat direction. In the y hat direction, you're going to have to do a little bit of integrating. Basically, go back, notice that in the y direction, dEy would be dE times sine of theta. And a lot of the rest of this stuff actually still works out okay. It's just that you have a second integral with this dE sine theta term in it. And you can basically go figure out what that integral is going to look like. I'm not going to actually do it for you because I'm sort of running up against the clock. And that in fact is it for this part of the lecture. So now we've covered electric fields. The next part is going to be looking at Gauss's law, which is sort of a nicer way of calculating both force and, for that matter, magnitude of electric field than Coulomb's law, although it tends to work well for certain geometries as compared with other geometries. It is in some ways a simplification. But this is it for electric fields proper. So I hope that you found this video helpful. I hope that if you watch the examples, that what I did was clear in the examples. And thanks for watching, and so long.